So here we go. Mathematical induction. We're taking a statement, dealing with series and things like that, and we're proving it through this principle. Here's the first example. You have Sn, which is the sum of the first n terms. So you have the sum of this particular type of series, and the statement is that this sum of this first n terms is equal to this particular formula. So if I want the sum of the first 12 terms, adding the first 12 terms would be the same thing as just plugging in 12 here. That's the statement. I want to prove it to be true. So if I want to prove it to be true, I'm going to use mathematical induction. Here's the process. Let Sn be a statement involving a positive integer n, which is what we have here. First step is to prove that S1 is true. Is it true for the first term, or when n is equal to 1? So let's start with that first step. So this is an example. So the first step is to prove that it's true for when n is equal to 1. So I'm going to plug in, so I want just S1, right? Just S1. So that means the first term. Well, the first term of this is 1. And I want to prove that that's equal to this particular formula when n is 1. First step is very easy. Is the first term of the sequence equal to this when n is 1? Well, let's see if I simplify. Is 1 equal to, so this is 1, I'm going to show my work, times 2, blah, 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 blah. So 1 is equal to 1, so that works for when n is equal to 1 for the first term. Now, the truth of the statement sk implies the truth of the statement sk plus 1. The second step, okay, I'm going to add kind of a third step to this. So the second step is to assume that the kth term is true, or I should say sk. Assume sk is true. The sum of the first k terms is a true statement with when n is equal to k here. So what I'm saying is I'm plugging in k for n. So if I want to find sk in that statement, I have 1 plus 2 plus 3 plus all the way to when n is k. And the statement is that that is equal to k times k plus 1 over 2. This right hand when n is k. Now I have to assume that this is true. I'm assuming that this statement is true, so that I can now prove that it's true for sk plus 1. So we show it's true for 1. We assume it's true for k, and now we have to prove that it's true for sk plus 1. But we're going to use this assumption to prove this. So here's the cool part of this. This is the part that I like. This is where the tricks come into play, and you might have some little like algebra manipulation, that's the fun part. So sk plus 1. So let's write this out. So I have 1 plus 2 plus 3 plus all the way to k, and then plus k plus 1 is the next term after the kth term, true? And this is the k plus 1 term. So I'm going to now replace n with k plus 1. So n is now k plus 1. So k plus 1 times, I'm replacing n with k plus 1. K plus 1 plus 1 all over 2. So what we are going to do here, here's the trick. We said that the sum of the first k terms is equal to this statement here. Well, I have a sum of the first k terms, and I'm saying that this is equal to this, right? K times k plus 1 over 2. But that's just this part of the statement. Now I have to continue. Plus k plus 1 should be equal to this statement, k plus 1 times, I might just simplify this, k plus 2 over 2. Right? So once you assume that it's true for k, when you're dealing with the k plus 1th term, which is the term after the kth term, the sum of that your k formula is within the k plus 1 formula. So I'm replacing the sum of the first k terms with this formula because I said that that's true. So I'm replacing that. Now I need to just make sure that these two sides are equal to each other, prove that they're equal to each other, and then I'm done. So this is the algebraic manipulation portion. The right-hand side of this is a single fraction, and the left-hand side has two separate fractions. So what I need to do is I need a common denominator to bring them together. So this one needs, this is a 1. So it needs a 2 on the top and a 2 on the bottom. So let me rewrite that. So now I have this k times the quantity k plus 1 over 2 plus twice this. 2 times the quantity k, I'll leave it like this for now, all over 2. And this is supposedly equal to this thing here, k plus 1 times k plus 2. I don't know if you see it already, but it's there, over 2. I'll show this next step. When I bring these two together into a single fraction, I have k times k plus 1 plus 2 times k plus 1 all over 2. And that's supposedly equal to this, right? Well, if you remember factoring binomials that k plus 1 is in common, I can factor out the k plus 1. And when I do that, I'm left with k plus 2 over 2 equal to k plus 1 times k plus 2 over 2, and I just proved this is true, and therefore that statement initially was true. Obviously, I need to do some more improvements. So this is called mathematical induction. Let me find another example